Hey everyone, welcome to the Explainer. Today, we're doing something really cool. We are forging a C-linked list completely from scratch. By the time we wrap up, you're going to have a literal masterclass under your belt in dynamic allocation, node architecture, and raw memory manipulation. So let's just dive right in. To build any kind of dynamic system, we've got to define our atomic building blocks first, and really understand why C desperately needs this dynamic data structure. You know how a rigid array forces everything to sit right next to each other? Well, a linked list throws that out the window. It actually scatters its elements, tying the whole thing together purely with pointers. We've got 4 distinct goals on our roadmap today. First up, defining a node structure using struct. Second, creating an empty list. Third, dynamically allocating new nodes using Malloc. And finally, securely linking those nodes together into a functioning chain. Basically, this is your complete guide to mastering dynamic data structures. So let's look at the anatomy of a single node, our fundamental atomic unit. Look at the struct node definition there. It's split into 2 parts. First, you've got your int data in the blue box, holding the actual value, right? Then, over in the orange box, there's struct node pointer. That is our pointer. Notice how the structure literally contains a pointer to its own type? We call that a self-referential structure, and it's absolutely crucial. This specific feature, a pointer reaching out like an arm to grab another node of the exact same type, is literally the only thing making a continuous chain possible. Now, every mighty chain starts with absolutely nothing. When we initialize our head pointer to null, we're creating an empty list. See, the head isn't a node itself. It's simply a pointer. It's the designated entry point to our entire system. You can kind of think of null as the system's ground wire. It's just a clear indicator that 0 nodes currently exist. Because of this, checking if head equals null is a mandatory safety check before you do anything else. If you skip that, your program is going to crash instantly trying to read data that just isn't there. We're shifting from the blueprint to the actual physical layout of RAM to see where these dynamic structures actually live. Okay, so you probably already know the stack is super rigid. It auto-deletes variables the literal second their function ends. But our nodes, they need to survive beyond the function that creates them, so they absolutely cannot live on the stack. They require the dynamic environment of the heap. We have to manually carve out space on this vast open matrix using the Malloc function. In that memory, it stays there securely until we go in and manually delete it using free. And this shows exactly why the heap needs a linked list in the first place. When Malloc secures memory, the operating system basically scatters your nodes wherever there happens to be free space. Like node 1 might be way over at address 1000, while node 2 gets dumped far away at address 2000. Because these nodes aren't sitting neatly side by side, that orange next pointer acts as a physical wire. I mean, it is the absolute only way the CPU can find its way from one piece of data to the next. Let's step onto the factory floor and execute the mechanical process of allocating, verifying, assigning, and linking. Forging a single node is a strict 4-step assembly line. Step 1, allocate the memory using Malloc with the size of our struct node. Step 2, verify. Never, ever assume your allocation succeeded. Always check if your new node is null to make sure your system didn't just run out of memory. Step 3, assign your data, like popping the number 10 into the blue box. And finally, step 4, terminate. You absolutely must set the new node's next pointer to null. If you skip this termination step, your pointer is going to hold random garbage memory. Your code will blindly follow that garbage into a catastrophic crash, which, is a really great way to ruin a Friday afternoon. Now, before we actually link them, we need to quickly talk about syntax. Look at the dot operator. That's used for direct assignment on regular struct variables. But remember, we're building on the heap now, and dynamic memory means pointers. So we gotta use the arrow operator, just a hyphen followed by a greater than sign. The arrow operator explicitly tells the compiler, hey, follow this pointer to its destination in memory and then access the data there. It is the absolute professional standard for pointer dereferencing in C. And this right here brilliantly illustrates the exact moment 2 separate nodes become a linked list. We start with a first node pointing to null and a second node pointing to null. The real magic happens with just one line of code. First.next equals second. You can visually see how this completely overwrites the first node's null terminator, replacing it with the memory address of the second node. Boom! The physical connection in memory is established. We've officially built a bridge. Watching this whole thing build sequentially is pretty cool. We start with an empty head. Then we create node 1, give it data 10, and a null terminator. Next up, we create node 2 with data 20, and we link node 1 right to node 2. We just repeat that process for node 3, continually updating that previous link. But hey, look at the teardown phase at the bottom. This is vital. What is built on the heap must eventually be freed from the heap. To prevent system crashing memory leaks, we literally have to use the free command on every single node before our program wraps up. Since manual labor doesn't scale, let's see how we automate all this architecture. So, once you have a chain, how do you actually extract data from the end of it? Well, welcome to pointer gymnastics. Something like head.next.next.data might look like a dense wall of code, but visually it makes perfect spatial sense. Each arrow operator is a literal physical hop across your computer's memory. We start at the head entry point. That first .next, that's hop 1, traveling down the wire to node 2. The second .next is hop 2, traveling the next wire to node 3. And finally, .data is our actual destination, pulling out the value 30. The CPU is physically traveling down these lines to retrieve your value. Now, try to imagine a list with 100 nodes. The amateur method creates 100 unique, hard-coded pointer variables. I mean, that is a total nightmare to maintain. But the professional approach, it uses scaling. We initialize a single reusable pointer called current and just set it equal to head. Then we use a while loop. As long as current is not null, we execute current equals current arrow to next. This dynamically slides that one single pointer down the entire chain, node by node, until it hits the end. It's clean, it's efficient, and it perfectly handles lists of literally any size. We need to adopt a really urgent, investigative mindset for this final stretch to look at the catastrophic, real-world consequences of sloppy pointer management. Seriously, treat this scenario like a flashing neon hazard sign. The head pointer is your absolute only tether to the entire linked list, floating out there in the heap. Look at what happens if you carelessly say head equals Malloc to create a second node. You overwrite the original head pointer. Instantly, the link to node 1 is severed. Cut. Node 1 is still sitting there taking up space in the heap, but your program has completely forgotten its address. It's just lost forever in the memory matrix, creating a totally unrecoverable memory leak. The rule here? Never move your head pointer for construction. Always use a secondary helper pointer. To avoid those kind of careless mistakes, professionals stop writing redundant code. Instead, we encapsulate that raw allocation logic right into reusable factory subroutines, like check out createNode. It handles the Malloc allocation, verifies the memory, safely initializes the data and pointer to null, and then returns a fully ready-to-use node. Then, createList can just take an array, loop through it, and repeatedly call our node generator, safely linking everything together with a current pointer. Doing it this way keeps those dangerous memory checks automated and completely out of our main program logic. You can consider this your mandatory pre-flight system diagnostic. Running through this 6-step memory checklist before compiling is going to prevent 99% of your linked list crashes. Step 1, include your dependencies like standardlib.h. 2, allocate your space with Malloc. 3, verify that allocation by checking for null. 4, initialize securely by terminating your node's next pointer with null. 5, protect your tether. Double-check that your head pointer hasn't been overwritten. And finally, 6, clean up by writing a free for every single Malloc. Okay, let's treat this final code block like a crime scene investigation. So the programmer wanted to link 2 nodes with values 5 and 10. They allocated the head, assigned 5. They allocated second, assigned 10. Everything looks okay so far. But look closely at that highlighted line. Head equals second. This is the exact moment they introduced a fatal flaw. By assigning second directly to head, the head pointer completely abandons the first node. The fix is super simple but absolutely crucial. To establish a link sequentially, you have to target the next pointer, writing head to arrow next equals second. Guys, that single missing arrow operator is literally the difference between a perfectly working program and a catastrophic memory leak crash. And just like that, you now know exactly how linked lists are forged from the ground up. We've tackled dynamic node structures, head pointers, heap memory, Malloc, linking, traversal, and how to dodge those fatal memory leaks. Honestly, these concepts are the absolute bedrock for everything else you'll ever do with dynamic data structures in C. But before we go, I want to leave you with a bit of a provocative thought. Now that we know our nodes are physically scattered across the heap, connected only by these thin little wires, how do you think we'd insert a brand new node right into the middle without breaking the rest of the chain? Think about the pointer gymnastics required to pull that off. Thanks so much for hanging out with me for this explainer, and I'll catch you in the next one.